You know, it's an honor to be here with all of you. Thank you very much. I'd like to talk about something that I hope will be interesting for you, but first, who I am. You know, I was born with passion to informatics, and now I'm a PhD, but when I was doing my research job, I was always thinking about practical applications, and probably that's why I'm here. I hope my practical applications will be interesting for you. I'm working on University of Technology in Rzeszów in Poland, and my research concerns distributed systems. For now, everything is distributed system, as you know, so that's one reason it will be interesting. I also use Ruby as a tool in my research, so that's the other interesting part probably. It's written in Ruby. I'm also an academic teacher. I'm teaching, among other things, I teach also Ruby and Rails. And well, we have a Ruby user group in Rzeszów, so if you wish to visit us, we are friendly people. You can come. We can discuss different things, and also we will have time after the presentations. What else? Personally, I have a wife and 3 kids, and I'm quite happy about it. Thanks. So, I need you to do a little bit TDD with me, okay? So first, the test. Who ever heard about a distributed system called the grid? Yeah, there are some people, but not many, and that's the intended failure, okay? I will provide quick implementation just to put us on the same page and give you my motivation. Imagine a large worldwide supercomputer where you can push whatever computations you need or use whatever resources you can find whatever resources you need on this supercomputer, so you don't have must have your large data centers, just use it and pay the bill, okay? But you know, I know you are thinking about cloud computing, but it's not a cloud computing. It's like you had one worldwide cloud, single cloud, with a lot of vendors, a lot of providers, a lot of users, but this supercomputer is just infrastructure in between. Like we have one worldwide internet with a lot of vendors and with standard protocols, okay? So it's a worldwide, super complicated distributed system to connect users with resource providers. Okay, that's what scientists, researchers were researching for a dozen or more years all over the world, for example in CERN. And at some point, cloud computing emerged out of nowhere. How did they know all the solutions? Well, that's how did they know, okay? It was researched during the work on the grid, and I had my opportunity to do a little bit about it. We were working on, I was working with people that were developing monitoring system for this very complicated system, just to provide something between standard developer tools and the applications. You know, you have debuggers, you have profilers, and if everything works on your local machine, it's quite simple. But if you have debugger on your local machine and application running somewhere in the world, you don't know where, you need to debug it. So you need something in between to deliver the information between the debugger and the application. And that was the monitoring system, the OCMG. It was meant also for interactive applications. We needed online monitoring, and you know, in the grid, as in internet, there was no central management. It was all distributed. So there was also no central management in the system. Parts of the system were shared between users, developers, applications, projects. Parts of this system were, of course, application specific. and we had quite tight security requirements there. And my job was to find a security solution for this. It was quite exciting. Okay, but that's not the topic of this talk. I did it, and when I finished, someone asked a strange question. Well, you know, this your security solution works. It will be okay. But it generates additional overhead. What can we do about it? We need this online monitoring, and you provide additional overhead. Will it still work or not? Or maybe it will be too slow. And then, you know, it was simple enough, and we had some, it was possible then to create some basic experiments, like, for example, what is the overhead for single secured connection in comparison to unsecured connection? I created some experiments like this, measured it, and we could look at the results of the basic experiments and decide that, okay, for the whole system, it will also work. The overhead is not killing will not kill the performance of the whole system. But it could be done for that system. At that point, I started to wonder, well, what if the system architecture would not allow us to derive these conclusions such easily? What if the system architecture was so complicated that we wouldn't know? After these basic experiments, we wouldn't know what will be the overhead on the overall performance of the system. And what we have now? We have now, for instance, microservices, and can you always tell what will be the performance of overall system when one or two of your microservices will start lagging? Well, so that was my goal from that moment. Because, you know, I know what we would do if this happened. You know, we are researchers, scientists. That's what we need. It's not a problem, you know, it's an opportunity. If we find something like this, we take one formal method, two formal methods, or a dozen formal methods, we model it, we simulate it, whatever, and then we publish it, and we have work for half a year or 2 years. We are very happy. But the real question is, what would you do if you face such a problem? You provided a solution, and client asks you, well, okay, but I won't deploy it until you tell me it will not kill performance of my application. No way to production. What would you do? Will the client pay for your time for half a year or 2 years until you learn a formal method and scientifically prove it will work? Sorry, I don't believe it's feasible, okay? So I wanted to find a way for you, for developers, to use formal methods without learning them, to give you a tool where formal methods are below and provide precise results, and you can use it easily. And that's what this talk is about, okay? So I will show quickly what's the approach, and then I will show you basic example just to catch how it works, how to use it, and 2 case studies. Okay, that's a lot, and you are tired. I'll do my best to lead you through this, these topics. Okay. I hope very much that you are not trying to read it. Okay, that's long but yet incomplete list of scientific research papers about how to do it. Will it be precise or reliable or not? If someone is interested, I will provide the list. You can read, you can discuss. I can talk about it from now till whatever you want, but not, okay, that's all about scientific part. What is the basics of the solution? I use simulation, so I simulate whatever you need to analyze to provide some results. Of course, to simulate something, you need to create a model. So we create model using Ruby-based DSL to make it as simple as possible and as flexible as possible. And well, this simulator is the hard part, the previous slide, I mean. There's the whole science that makes it precise. And from the simulation, we get results that are saved in a file, and then we can iterate over the results with Ruby iterators to gain provide some indexes to compute to show how it works. Or well, what's the basic example? Very basic example. We will get a web server, web clients, and some resources to run everything, just to see how to model it. Web server, what is a web server? Generally speaking, because if we need to model something, it's always about generally speaking, how it works. Generally speaking, web server program is something quite simple. It does nothing until it receives some data. We call it a request. If it gets a request, what does it do? It processes the request on CPU for some time, and that's the CPU tag, the statement there, and thereafter it sends response to wherever the request came from, right? So that's all. That's complete model of web server program. Of course, if we would like to know how much it took to process the request or every subsequent request, we should put two more statements here. These are probes. Start saves start time with some tags, and with corresponding tags we have start stop, and then we will be able to iterate over the start and stop of every request. Okay, we have complete model of a web server program. About web client, it's much more complicated because we have two events. Generally, web client will send some requests and will do something when responses arrive. Okay, let's get deeper to see the send event, sending the request. We do some CPU processing to prepare the request. Then we send the request to a target. It will be a web server. And next 4 lines is just to count the sent requests and decide if we should send another request or not, with a delay, probably. Okay, that's all. On then data reception, we can do different things. In this case, we just log it to know that something happened, and we save this in stats file information with timestamp that response was received. We, of course, need some resources. How to define resources? We need nodes to run the programs. So that's how we define nodes, in this case too. And we need some networks to connect the nodes. That's all we need to define. It's very slow, sorry. I mean, the networks are slow. And we need routes to know over which net segments between which nodes we need to, which network segments we need to go from one node to another. And finally, when we have programs and resources, we just need to start the programs on resources. So we define new processes. These are 2 client processes running the wget program, and 1 server process running the Apache server. When we start the processes, we just define where which process where should be executed. Okay, that's complete model. That's complete model. We save it in model RB. To run it, we need a little bit more Ruby code. We define empty class deriving from RBSim experiment, and we can use an object of this class to load the model and start simulation. And when simulation is finished, we just save statistics in a file or append the statistics in a file to a file. When simulation is finished, we can process the simulation statistics. We can implement it in this experiment class. It was empty for starters, but now we can put something useful there. Inside this class, we define methods, and we have objects available, appstats and reststats for application and resources statistics, and we can iterate over different kinds of events saved during simulation and do whatever we need. In this case, I'm just printing the results on screen, but we can aggregate them using some kind of into some kind of statistics, or just create CSV file or whatever. Sorry. Then we can use this class to load statistics from file and to use these statistics. Okay, that's the basic example. It's not like your applications, certainly, but it defines the main components. I believe there is no boilerplate code. Whatever we need to write is necessary to implement what we need. And it's, and it's like 60 lines of code, everything, all the model, okay? But I think case studies will be much more interesting. Well, the first case study is about EuRuKo. I'm not sure if you followed the case between Genius or Rap Genius and EuRuKo. Did you? Some of you did. I hope EuRuKo won't punish me for bringing this up. Well, you can always go to this link and find the blog post together with comments. It's very interesting reading. No matter what you think. What is it about? Well, EuRuKo, I'm not sure if you know about EuRuKo architecture. You would certainly use it, but did you deep dive inside? I tried a little bit. Generally, there are dinos below, and above is something they call routing mesh, and when someone sends you a HTTP request, it hits the routing mesh, and the routing mesh decides which Dino should serve the request. Of course, the Dino is selected on specific algorithm. First, it must belong to your application. But if you have more than one Dino, what then? Well, at the beginning, EuRuKo was talking a lot about its intelligent routing and telling that your Dino will never receive more than one request at a time. So it was idle. It could get request. If it was not idle, no request was sent to this Dino. Okay, so it was really perfect load balancing. At some point, they switched to something called random routing. So no more intelligent routing. When a request comes, it's randomly assigned to one of the Dinos, no matter if it's idle or not. So why? Why? For EuRuKo, I don't know. I didn't ask them. Maybe I'll take a chance. Maybe they'll know. But it's easy to imagine that the random routing is perfectly scalable. You can run as many HTTP routers as you wish. Okay? Unlike in case of intelligent routing, where you can have many HTTP routers, but you also need a place to store all information about busy and idle Dinos. So it's a bottleneck. And second thing, they don't have to detect if Dinos are busy or idle. For Rails, it's simple, but I believe that for event-related solutions like Node.js, it's not so simple as for Rails. So that's a simpler solution for them. But what about the client? First thing, is random routing really worse? That's quite easy question. It's certainly worse. It should be worse. But really harder question is, how much worse is it? Because if it's so much better for the infrastructure, maybe it's worth to switch to random routing. Maybe it will pay off. So well, again about this blog post, you can find there description of a simulation performed by the author using our programming language. By the way, description of simulation, of results, conclusions, and so on. Read it, it's useful. I decided to repeat this simulation, this modeling, first to learn from the best. I like the extra. Sorry. So the first, it's not an offense to repeat someone else's experiments. It's just a good practice. Second, I wanted my own angle to look at this problem. What should we model to test this situation and see the results? HTTP client, server, random router, intelligent router. That's what we need, okay? But well, I've shown you the basic example before, and we had the HTTP client there, so we don't need another one. We've got it already. We had the server, we have random router. We have to define random router and intelligent router. That's what we don't have. Random router is a simple device. When it receives a request, it just takes random server from a list and forwards the request there. That's all it does. So it's quite simple to model. If it receives a response, then it just forwards the response to the correct client, and it will work. It will work. The intelligent router is a little bit more complicated. So I implemented it with two events. First event, data received. When data is received, if it's a request, then we just put the request in a request queue, and we will try to process it. If it receives a response, what do we do? First, we got the response, so we save in the list of idle servers who sent us the response, because the server is idle. Then we forward the response to proper client, and we try to process another request, because we have a new idle server, so maybe we will be able to process another request. How does request processing look? It's also simple. When we have an idle server and a request to be processed, we take first request from the queue, first server from the list, forward the request to the server, and maybe we will try to process another request if it's possible. All right. All right. We also need resources. I won't show everything, but I just remind that it's Ruby-based DSL, so we can use loops and different Ruby-related things just to model large infrastructures if we need. What about the results? What about the results? Are you curious? That's the yellow one is for random routing. Blue one is for intelligent routing, and the application is not loaded at all because it's loaded in 1/3, so it's not allowed. That's how it looks like. Request service times. For intelligent routing, we have all requests, all 10,000 requests served in a slot of 50 milliseconds. For random routing, well, it doesn't look so well. So good. Some requests take up to 3 seconds. And the application is not yet loaded. What about bigger loads? For 50%, intelligent routing is still okay, but the random router, even worse. If application is really significantly loaded, it's even harder. We have some requests served in 18 seconds. But, well, analyzing histograms is, well, it's tricky and it's not convenient. Maybe I'm just trying to talk you into something that is not there. It's easier to compare numbers than histograms, so maybe we will compare numbers. Abdex, you use Abdex? We can compute Abdex from the results of simulation, and we can put it on a graph, so let's see it. That's how it looks for intelligent router and for random router. You see that, well, even if application is loaded in 90%, the user experience is better than for random routing and application loaded in 30%. You see this? That's how it looks like. So, yes, well, the random routing is much worse for the client. But at the moment, we have our result, we have our conclusion, but at the moment something other came to me, and it was not very elaborated. Maybe we could do something in between. Maybe we could take the intelligent routers because they are better, but remove the bottleneck, the repository of idle servers, and run a lot of intelligent routers independently. They would be much worse than true intelligent routing, but maybe it would be better than the ordinary random routers that do not know anything about idle and busy dynos. It's not very elaborated, but you know, simulation is cheap. Let's check it and learn something. That's the situation for 10 intelligent routers and one random router. That's the situation for 20 intelligent, independently running routers. 30. I tried also 40 and 50. You see, well, it's probably not worth to try to deploy such solution because the user experience won't be much better. And what is 20 or 30 routers for such a big infrastructure like EuRuKo? Okay, that's another conclusion from this simulation. What we can conclude from this case study. First, we have reusability. If you ever modeled a web server, you can reuse it wherever you want. If you modeled a web client or some load balancer, you can reuse it next time. Second, it's flexible enough to implement whatever algorithm you devise to into your application and need to test. You can watch the results on different levels of abstraction. You can use histograms, you can iterate over every single request time if you wish, or you can just compute some indexes like updex and have one number as a result of whole simulation. And if something comes to your mind, you can just test it. What would happen if I did something strange? And you can test it much more easy than if you tried to deploy real application and do some real benchmarks. And the second case study, it was also connected with EuRuKo, but a little different case. It was the question, should I scale my application on EuRuKo or not? It was connected with two kinds of dynos that EuRuKo offers. Single dyno, a little bit slower, less RAM, less memory, and the double dyno. And it concerned the application that was implemented in Rails, running on Unicorn, and it was unlike the others because it was not database intensive, it was CPU intensive. It did quite a lot of data processing. It was running 6 single dynos, and the question was, will we gain something if we switch to 3 double dynos, from 6 single to 3 double? The question was, because it was running Unicorn, you know, Unicorn have this master process which does real load balancing for its workers. It sends one single request for each worker to process and never sends another if the worker unless the worker responds. Okay, so we could gain something, some performance from this load balancing. We hoped for this. Well, you see, it's quite like the old intelligent router of EuRuKo. So we had opportunity to exploit this situation, but we were not sure if it will work. Of course, we could test it on production, but it wasn't a good idea, I believe. I don't know what you think. Testing on production. It can teach us a lot, yes, that's right, but maybe there are cheaper ways. So we could have twice faster dynos, twice fewer dynos. We could run more unicorn workers per single dyno because the bigger dynos were more capable. But we would have same number of unicorn workers per application, same price. We would have more memory for peak situations, which happen sometimes. And maybe we will gain something from the load balancing. We could get application parameters from New Relic, so it was quite easy thing to get what do we need to model to have it. HTTP client, HTTP server, random router for Heroku, and unicorn master process, 4 things. We already have HTTP client. We already have HTTP server. We already have random router from the previous test. And well, unicorn master process is like Heroku intelligent router, and we already have model of Heroku intelligent router. Well, we can reuse all the items we had before, just have to glue it into new situation. So that's what we did. We also needed to model dynos, and it seemed quite basic things to do, but here a problem appeared. If we model the single dyno like this, a dyno with single CPU, how should we model the double one? Is it a dyno with twice faster CPU, or is it a dyno with two more CPUs? Like this. And, well, the problem is that Heroku documentation doesn't answer this question. I don't know if you can derive an answer from this table. I cannot. It's supposed to be twice faster. The double dyno is supposed to be twice faster, but, well, how? It doesn't say it. So the problem is, how do they scale the dyno? Horizontally or vertically? But real problem is, does it matter? Maybe it doesn't matter for this very application, and we shouldn't care. How to check if it does matter? It's simple. Simulate both situations. We can do it. Maybe one of them is quite artificial, but it doesn't matter. We can simulate both. So these are the results. This is for horizontal scaling, and we can see that if they are scaling the dynos horizontally, we wouldn't gain anything. Because we can run like 2-3 dynos for 2-3 unicorn workers for a single dyno, and 4 or 5 for double dyno, so the performance for the user will be comparable. But if they scale dynos vertically, the situation is completely different. Okay, we would gain a lot. So what could we do? Well, if it does matter how the dynos are scaled, we confirmed it quite easily. But how to find out how the dynos are scaled? Documentation doesn't help. Believe me that CPU info, well, only adds to confusion. So what can we do? We should experiment. No way another. You know, I cannot call Heroku and ask them questions. Maybe you can, but we couldn't. So we decided it will be easier to experiment on Heroku dynos. We just bought single and double dyno, and what? First, we run a single CPU intensive task on the both types of dynos and measured time, runtime. And we got comparable times on both dynos. We could have some conclusions from this situation, but we wanted to be sure. So we did another test. We ran 16 CPU intensive tasks at the same time on each type of dyno and measure the times, and that's what we get. That's what we get. And if we compare the sum of user and sys time with real time for both situations, we can see that single dynos have 2 CPUs and double dynos has 4 CPUs. Okay, that's how we should model it. So, okay, now we know how the dynos are scaled. We can take the simulation results and derive conclusions that it's not worth. It's not worth to rescale the application because we won't get better performance from this rescaling. But well, okay, we've got our results, but I was running something on EuRuKo. I was, using their CPUs. They will now charge me, and I had to do it on my own with my own credit card because paperwork on my university to pay for EuRuKo, it's too hard to do and not worth. So what about the bill? It was hard, really. I believe EuRuKo wouldn't claim it. Thank you, EuRuKo. Well, what's the result of this case study? First, we used reusable components. In fact, the first results were the matter of one evening, quite interesting, but not very hard work. It didn't require very hard work. Of course, I was working longer then, to be sure, to test different things, but after one evening, we knew quite a lot about the problem. We, using simulation, tested different alternative configurations, and thanks to this situation, we were able to identify the factors that were crucial for performance, and then we could use really basic experiments, real-world experiments, benchmarks, to test only the crucial factors. We didn't have to deploy a complicated environment to do a complicated benchmarks. So, the summary. It's easier, cheaper, and faster to do it by simulation. Even if you don't know all things at the beginning, it's easier, even if you, at the end, will be forced to do some experiments. To do it, you need to describe your application using DSL, but I tried hard not to put some boilerplate or other inconveniences in the modeling language. We can test different alternatives if we wish, even if they are not very elaborated. Below it, there's no magic, there's quite a lot of science, so, well, it really works. It's really precise, it's reliable. Well, this is a unique offer. If you need such a simulation, I can be your service. I'm looking for practical applications for this, so I'm sure we will find a solution to do it. You will get your results, your information. I will get my case, one or two or more. Feel free to approach me. And one last thing. You know rubber duck debugging, yeah? So, this simulator is like rubber duck on steroids. You are coming to this rubber duck and explaining your problem using this DSL. And if explaining the problem doesn't help, you can just run the simulator and the rubber duck will talk to you. It will give you some results. And then you will see the results and you'll be able to explain the problem again to the rubber duck to get more precise and better results. And so iteratively, you will get something in between I don't know anything and what I showed you on the presentation. You will probably never need to come to this form of results I showed you unless you have to show it to management or a client, okay? Because when you are halfway between I don't know anything and this, what I showed you, you will be wise enough to ask yourself, well, I don't need a simulation. That problem is so simple. But it was not simple at the beginning. It's just a rubber duck. Thank you.
Great talk. Thank you. Thank you. So we have a coffee break now.
Sorry?
Or do you want to take questions?
Sure.
Okay, so we have time for one question.
Is the project open source, or where can you get it?
I was waiting for this question.
I had
Thank
the
you.
same.
Thank you. You know, it's a little bit tricky. It's not open source, or maybe it's not yet open source, because when I'm employed by university, then university owns a part of rights to this project, but I'm in a process of buying this part for me, and then I will be able to decide. So let's hope for the best.
Thank you. Thank you.